This figure plots the change in Gibbs free energy versus mole fraction for a non-ideal solution. And when we mix two liquids together, the Gibbs free energy decreases, and if it were an ideal solution, kind of solution that we use in Raoult's law, for an ideal solution, the change in Gibbs free energy, IS indicate ideal solution, is the sum of mole fractions log of mole fractions. And this, of course, comes from the entropy term for entropy of mixing. It's in the Gibbs free energy because delta H for an ideal solution is 0. So if we look at this figure, change in Gibbs free energy, we can see that the change is negative, that when we mix at different concentrations, the Gibbs free energy always decreases. Now, what we're interested in is a case where we have positive deviations from Raoult's law. So what this means is if xi gamma I, where gamma I is the activity coefficient, pi sat yip, this is the modified Raoult's law. So when we talk about positive deviations, we mean gamma I is greater than 1, and so the pressure above a liquid mixture is higher than that predicted by Raoult's law. So delta G of mixing for a real solution has the ideal solution term and another term that we call excess Gibbs free energy, and this excess Gibbs free energy is RT, the sum of xi log gamma i's. Since gamma i's are greater than 1, this is a positive term, and if this term becomes positive enough, we can get to the point where we have phase separation. So keep in mind, we typically get the gamma I values from some model of the solution. So some model where we make a few measurements, fit it to the model, and then calculate the gamma values at other compositions. If the G excess, which is greater than 0 for the case of positive deviations, if it's large enough, then we can get phase separation. And now we would end up with two liquid phases in equilibrium. Let's look at what that looks like on the Gibbs free energy plot. Here, this figure indicates phase separation because we have two minimum in the Gibbs free energy versus mole fraction plot, such that I can draw this straight line, which is tangent to the curve at the 2 points indicated by the blue and the green circles. And why this is important is because if I look at, for example, this composition, the Gibbs free energy here is lower than the value from adding the excess Gibbs free energy plus the Gibbs free energy for an ideal solution. Well, if it's lower, that's a more stable phase, and so that means we're going to end up at this point. Well, how do we get that point? We take a linear combination of these two phases. And we basically can use the lever rule to determine how much we have of each phase. If we are over here, of course, it's mostly the phase represented by the blue dot, and if it's over here, it's mostly the phase represented by the green dot. So we can look at an interactive simulation that draws these curves to get a little better idea how this changes. So here's the interactive simulation that shows the change in the Gibbs free energy. Mix two liquids, and the representation on the right is a cylinder that contains, in this case, one liquid, and the mole fraction corresponds to the value of the black dot. As I lower the temperature for these two liquids, let's lower it just a little further, notice we get to the point where we can draw a tangent line to the curve such that between the blue and the green dots, that tangent line has a lower Gibbs free energy than that predicted by our model that we're using to get our activity coefficients and therefore calculate the change in Gibbs free energy. And so that means we're going to have a more stable equilibrium condition when we have two phases present in equilibrium, as indicated by the figure on the right, and the mole fractions of these two phases are one corresponding to the blue dot and the green dot. If the temperature decreases further, it becomes even more noticeable. So now, very clearly, we have two distinct phases. And the relative amounts, if I change the overall mole fraction, then you can see if we get closer to mole fraction of the green dot, then we have more and more of the phase with the mole fraction of 0.76. So the lever rule can be used to determine how much we have at each phase along this tangent line. And lowering the temperature increases the excess Gibbs free energy. The liquids mix even less as we lower the temperature, and we get more phase separation.